So the rod is not massless in this situation. The rod is also having a mass. Mass of the rod big M and mass of the bob is small m. Okay. This rod is rigid. Means under the weight of this bob, the rod will not collapse. Okay. And the length of the rod is also known to you. It is L. Question is, what minimum velocity should you impart on the bob in horizontal direction such that it can complete a vertical cycle? Let the velocity be v. At the highest position, the bob has maximum chance of falling. At the highest position, weight of the bob will be balanced by force of compression developed in the rigid rod. Okay, so at the highest point, velocity of the bob is 0 for minimum velocity imparted at the bottommost position. So you have imparted minimum velocity, so the bob will rise, and at the highest point the velocity of the bob will come down to 0 for minimum velocity. If you impart a velocity greater than this value, then the bob will cross the highest position not with 0 velocity but with a velocity greater than 0. But we are considering a situation in which you have imparted minimum velocity to the bob such that it can go round this side. Okay. So at the highest point the velocity equal to 0. Now we go for balancing energy. This is the lowest position A. This is the highest position. Since there is no non-conservative force, total energy of bob plus rod, total energy of bob plus rod system at A equal to total energy of bob plus rod system at B. Okay, what is the total energy of bob plus rod system at the lowest position? The whole thing is actually rotating. There is no translational motion involved in this. The whole system is actually rotating. So what is its kinetic energy? Only rotational kinetic energy. Rotational kinetic energy of bob plus rod. Is it okay? Whole thing is actually rotating. There is no translational motion. Rotational kinetic energy of bob plus rod at A plus potential energy 0, kinetic energy 0, potential energy mg into 2L plus potential energy of the rod, center of mass has gone to this position, mg into L, mg into L. Okay, or half m L square. This is the moment of inertia of the bob plus moment of inertia of the rod into omega ml square by capital M, ml square by 3 into omega equal to V by L omega square. This is equal to mg into 2L plus mg into L. Okay, so we can easily calculate V now, or L square will cancel, V square m plus m by 3 equal to 2 into 2 mgl plus mgl, or V equal to 2gl 2m plus m divided by 3m plus m into 3 whole root. First point is, at the highest point velocity becomes 0 for minimum velocity imparted at the lowest position, because the weight of the body will be balanced by the compression produced in the rod. This is the first point. Second important thing is, we will apply energy conservation. There is no non-conservative force, so total energy of the system, what is our system? Bob plus rod at the position A is equal to total energy of the system at the position B. Next important point is, there is no translational motion involved in this case. The whole thing with bob is only rotating. That's why kinetic energy part is given by this expression, half into moment of inertia of the system, moment of inertia of the bob, this much, moment of inertia of the rod about this axis of rotation is this much. Then how will you get omega? Since you know the linear velocity of the end position, the angular speed omega is given by v by L whole square. Okay, and what is the initial potential energy part? 0. Why is it 0? Because we are measuring height of the bob from this position. So initial height of the bob is 0, and we are measuring height of the rod from this position. For rod, you have to measure the height of what? Center of mass. Do not forget that. For the rod, you will measure the height of the center of mass. So it is 0 in the initial position. Finally, center of mass has gone to this position. So what is the final potential energy of the rod? mg into L. This distance is L. And what is the final potential energy of the bob? mg into